I think our next talk is the topic is the quality assurance of deep learning system. Let me introduce the speaker first. Xiaofei is the assistant professor in SMU. Previously, he was a postdoc in NTU under Paul Liuyang Group. He researched mainly focused on program analysis, software testing, verification, and quality assurance of the AI system. I passed it to Xiaofei.
Thank you for the introduction. So good morning, everyone. So today I'm very happy to be invited to give a talk about the quality assurance of deep learning system. So for me, actually, my background is traditional software engineering. So how to test the software, how to find the bugs and vulnerability in traditional software. So today, I'm really to give some experience. So how to apply the software engineers, so experience and ideas for the quality assurance of the deep learning system. Okay, so first the background, right? So you know, so now, so the AI and the deep learning have been applied in many applications. So autonomous driving, right, smart devices, right? So in particular, it has also been widely used in the cybersecurity domain. So for example, to detect the malware, to detect the intrusion. Okay, so here we want to use the AI to guarantee the security, cybersecurity. How to guarantee the security and the quality of the AI solution, the AI model used, right? This is another problem. So like the traditional software, right? It can have the bugs and the vulnerabilities so that can be exploited by attackers to attack the system. So actually, the deep learning system also, right? So is vulnerable, especially for the adversarial attacks, right? So you know, so for example, right? So this image is a pig, right? After we add the minor perturbation, finally it can be predicted as an airline, so with a very high confidence, so 99% probability. So when such attacks happen in the safety critical and security critical domain, right? So scenarios, so it can cause very serious consequences, right? Like the autonomous driving. So for this traffic sign, right? We add some noises in the environment, then finally it can cause serious consequences. Or in the safety security, so critical application like the malware detection. So attackers can exploit such vulnerability to bypass the checking, right? So for example, to attack and to avoid the detection by the AI model. Okay, so the quality assurance is very urgent needed. So while we are talking about the wide application of the AI system, actually the mainstream media is also reporting the weakness of AI, right? So like the single pixel attack, so only change one pixel, the image can be misclassified, right? Or like the audio attack, right? The attackers so insert some noises in the environment, then the audio, right, so will not be correctly translated to the text. Or like the autonomous driving, right? Or like the deepfake, so how to detect so the fake images. So actually last year, so AISG so held the competition about how to detect so the deepfake images and deepfake audios. Okay, actually, so for the traditional software, we already have some techniques, tool chains, right? So to guarantee the quality of the software. So for example, the software testing. So how to test so the traditional software. So after you develop the software, you need to test it. Okay, so the program analysis. So how to analyze automatically, right, understand the semantics of programs. So the software verification, so how to verify this software is correct. So there's no bug, right? So the debugging, how to automatically identify the root causes of the bugs, how to fix these bugs, and the code review. However, so these techniques cannot be directly applied into the deep learning models or the deep learning system, right? So due to the fundamental difference. Okay, so in traditional software, right, so the software is written by the developers as a source code. Okay, so the source code has a deterministic so logic. So for example, the source code can be represented as a control flow graph. Okay, so as the developers, we know if this condition is true, it executes this branch, right? Otherwise, it executes the else branch, right? So this is deterministic. So when there are some bugs detected, so the developers can easily debug the code and fix the code. However, for the deep learning system, right? So now the logic determined, right? So depends on the deep learning works as well as the parameters trained from the training data. So this is the new data-driven software. So as a developers, so we just collect the data, right? So we write the training program, we design the deep network architecture. So then the parameter will be automatically trained. Okay, so even for the developers, so it's very difficult to understand the right so logic right? What is the logic learned in the model? So yeah, so most of the time we call it the black box models. So when we find some bugs, so like the other examples, so even for the developers, so they are it's very difficult for them to fix this bug, to understand why, what is the root cause, how to better fix this problem. Okay, so this is the difference between the traditional software and the deep learning software. So this diagram shows software development life cycle. So in traditional software engineering, so we have the software development life cycle, so like the requirement analysis to software design, to the implementation, to the testing, to the deployment, to the maintenance, right? So this is the whole life cycle. So similarly, for the deep learning software, it also has such a life cycle. So here, I really show the two major parts. So one is the software development, another one is the deployment. Okay, so for example, so for the development, we first need to collect the data, right? We need to design the deep network. Okay, we need to design, right, so some parameters, and then we can train to the deep network. Okay, so this deep network need to be deployed into the different platforms or environments, right? So like the migration, so some platform migration and the quantization, we need to optimize and compress so the models such that it can be run in the environments so with a limited resource. Okay, so during the whole process, right, so the issues can happen. So in each step, so for example, your data may not be good. So there are some poisoning data. All the data is not balanced. Okay, all the architecture is not suitable for such task, or the parameters are not good. So which can cause so the model, the quality of the model is a concern. So for example, some fairness problem, so robustness problem, or so bias backdoor problem. Okay, so your model is not robust, can make the incorrect decision. So even this model is a perfect model, right? It's well tested. So when it is deployed into the different environments or the different platforms, it can still cause some issues like the capability issue. So it means for the same input, so the prediction results in the development environment and the deployment environment will be different. It can be caused by the frameworks, so platforms and devices. So for example, your model is trained by the TensorFlow, but you want to deploy it into the PyTorch sometimes, then you need to convert to the model. However, due to some inconsistencies between the different frameworks or some bugs, for example, in PyTorch, so in TensorFlow, so their prediction can be different. Or even for the same framework, like the TensorFlow, right? If you use a different versions, so the results can be different. Okay, so when you really deploy such problem, you need to consider these issues. Another one is about the platforms, right? So you want to deploy in the, for example, you train in the Linux, you want to deploy in the Windows or in the iOS or in the Android, right? So due to the difference between the operating systems, right? So their calculation can be slightly different, which can affect the predicted result. So similarly for the devices, right? So the hardware, so like the IoT device, right? So like FPGA, right? Different hardware can cause the minor differences in the the floating point calculation. So finally, it can affect the prediction. Okay, so I think in the last 3 years, so we conducted research on the whole workflow. So from each step, so we propose the techniques to provide a full stack automated testing and analysis solutions for the deep learning system. For example, so in the data level, right, so we need to guarantee the quality of the data. So we apply the mutation idea and the uncertainty idea to analyze the sensitivity and the quality of the training data and the test data. So after the model is trained, we regard the model as a software, right? So you need to test the software before it is deployed, before it is really used. You need to, right? So like the traditional software, you need to check whether there are some bugs, there are some issues. Okay? So here, yeah, for the testing, the first thing is we need the testing criteria, because testing is an infinite process. You can always, right, so generate test cases. So the number of the test cases can be infinite. Okay, so here the testing criteria will measure how many behaviors, right, so these test cases can cover, or how sufficient is the testing process. Okay, so for example, traditional software, we have the line coverage, we have the branch coverage, so how many lines of the code can be covered by these test cases. Right, so similarly, we needed to design the testing criteria or the coverage criteria for the deep neural networks for the testing. So we developed the Deep Hunter, so this is to test the feed-forward neural network, and the Stella, it is to test the recurrent neural network. Okay, so after the testing, we can discover some bugs, right, some incorrect predictions. So then we need to fix these issues. So we developed the deep repair to repair the feed-forward network, especially for the CNN. And the RN repair, yeah, it is to repair the recurrent network. Okay, so here these tools are developed for the deployment. Okay, after your model is deployed in different environments. So here the diff chaser, it is a differential testing framework to identify the inconsistencies between the development environment and the deployment environment. And the audio, this is another testing tool, which is to discover the bugs in the deep learning frameworks. So for example, we have discovered about 30 bugs in the TensorFlow and the PyTorch. Right? So if even your model, right, so it's very good, perfect. But if your framework, there are some bugs, so finally the whole system is not secure. This is like our compiler. Right? If your code, no problem, but there are some bugs in the compiler, so finally the compiled model is not correct. Okay, so this is the whole process. So today I will merely introduce 3 of these works. So one is about the testing criteria, another is about the testing, and then the repair. So first, this is the neural path coverage. So based on characterizing the decision logic of deep networks. So as I mentioned before, so the testing criteria is to measure how many behaviors covered by the test cases. So how sufficient, right, for this testing. So in traditional software, right, like the line coverage, branch function path, right, we generate a lot of test cases. We want to measure how many lines of the code, how many functions, how many paths can be covered by these test cases. However, so this standard criteria cannot be applied for the deep networks because in the deep network we don't have the model. Right? We don't have such a structure, so we need to design the new testing criteria for the testing. So recently, some structured deep neural network coverage criteria have been proposed, like the neural coverage. It measures how many neurons activity, so by the test cases, by the inputs. So the deep gauge, so this is a set of the fine-grained neural-based coverage, so like the KMNC, so this is a K multi-section neural coverage. Okay, so the neural coverage only consider activation or not. But for the KMNC, it splits the output of the neurons in many buckets and then measure how many buckets can be covered by the test cases. Or like the NBC, this is the neural boundary coverage. It only considers the boundary of the neural output. So the deep CT, so this is the combination testing criteria. So for the previous two, they only consider the behavior of the individual neuron. But the deep CT, it combines the behaviors of the multiple neurons. Okay? So however, the existing study has shown the problems for this structure's deep network coverage criteria. So one concern is they are black box. So for example, it's not easy to understand why the neural activation can be used to measure the coverage. Another thing is they have demonstrated, so this coverage are not, so this coverage criteria are not correlated with defect detection. Because for the testing criteria, we want to apply this criteria to guide the test case generation. So this is the motivation. Okay, so fixed on these two challenges, so in this work we propose the neural path coverage. So this is follow the traditional software testing idea. So in the left part, so let's see the difference between the traditional software and the deep learning software. In the traditional software, right, so we have the very, so this is the structure, so it's very easily to be understood, right? If this line is covered, right, this line is covered, so we can calculate the line coverage. If this branch is covered, we can calculate the branch coverage, right? So for the path coverage, so in this program we have 2 paths. Okay, so the path actually can represent the functionality or the business logic in the program. So for example, in this software, this path may handle the login. So this path may handle some other, right? So logic, for example, to list the user information. So this path can handle the error handling, so logic. Okay, so each path can represent the one function of the program. Okay, so using the path coverage, we can maximize the coverage on the different functionalities to test the different functionalities. However, in the deep neural network, we don't have such a structure. Right? So the line coverage, the path coverage cannot work. So you can see, so here, all these neurons are fully connected. Okay, so we cannot measure, okay, so this connection is covered or this one is not covered. Okay, so motivated by the path coverage, so in traditional software, so here we want to extract the path in the deep neural network. Okay, so let's say this yellow path may be responsible, may handle the decision for the tag images. Okay, and this red images, right? So this red path may handle the dot images. Okay, so then we can try to extract such a similar path. So to understand this path, we can convert, right? So this path to a program. Okay, so this program could be easily understood. So here, give any input x, we can extract the feature from x. Okay, so if the feature is close to a cat, this program will return the cat. Otherwise, it will return the dog. Okay, so in this program, these two paths are more explicit, right? Actually, right, so they are consistent. So this program shows what we want to do. We want to extract the feature, the path that can represent the decision logic for the deep network. And then we want to generate the test cases which can cover many different paths, which can cover many different decision logics. Finally, we can discover the errors. Okay, so this is the basic idea. So let me give you more things about the semantics of the deep network decision. So here, the path actually can represent the decision logic of a model. So for example, right? So here, this red path represents the white dogs. So how to recognize so these are dogs. And this green path can recognize, right, so the yellow dogs, and these two paths can recognize the different kinds of cats. Okay, so this is the semantic of the path. So this is the overview of this work. So we design the testing criteria. So the first step, so we collect the model and the training data. So you know the model is trained from the training data. So the training data can reflect so the decision logic to learn from this training data. So for each training data, we can extract so the path. So this path can represent, okay, so the logic learned from this training data. Okay, however, the problem is we have many training data. For example, 10,000 training data. So then we have a lot of paths, right? So it is not scalable for the testing, right, to calculate the coverage. So we need some abstraction because, right, so the deep network is assumed to be general, so which can handle some similar inputs. So in step 2 and step 3, we do the abstraction to build the abstract path, which can represent the logic for a set of similar images. So for example, the step 2 is intra-class path class G. So for example, we have the class dog, we have the class cat. Actually, some cats, some dogs, they are very similar. So like the white dogs, right? So like the black dogs. Okay, so they have some common features which may the deep network can have the similar decision logic to predict, to recognize so these images. So in the second step, so we extract, right, so the paths for each training data, and then we cluster so these images in the same class to the different clusters. Here the basic assumption is, right, so if the images can be clustered into one group, so they have the similar decision logic by the deep network. Okay, so finally we can get the class 1, 2, 3, many clusters. Each cluster, so they have the similar decision logic. And in the step 3, right, so in each cluster, we may have so a lot of paths, but they are very similar. Okay, so in the step 3, we will merge so this path to one abstract path. We select the common neurons which are important for the prediction of these images. For example, right, so this is yellow cat, right, so this is white dogs. Okay, so finally we can generate, right, so some abstract paths, so which can represent the decision logic learned from the training data. So the number of the abstract paths is very little. It's very few, right? So because we do some abstraction. Okay, so this is abstract paths we extract from the training data. Okay, so based on the abstract paths, then we define the testing criteria. We want to measure, give the new test cases, so how many new behaviors can be covered compared with the learned decision logics. So let me give you one example. So give a new input, we can extract the concrete path. Okay, so then we compare this path with existing abstract path. So for example, if this path is the same with the red one, it means, right, so this decision logic has been covered by the one of the training data or some of the training data. If this path is very far from the existing abstract path, it means the new behavior has been discovered. Right, so the new decision logic has been triggered by the new test case. Okay, so for the testing, we want to maximize the testing, the coverage. It means we want to maximize the behavior, the diversity. We want to generate so the test cases which can trigger so the different kind of decision logic of the model. So here are some more detailed things about the definition of the two neural path coverage. Okay, so here the basic idea is give a set of test cases. We want to measure so the distance between each test case and the existing abstract path. And then we want to, because the distance actually is a continuous value, it cannot be used to calculate the coverage. So we do the abstraction, interval abstraction. split the distance into some buckets. So for example, from 0 to 1, right, we can split to 10 buckets, then 0 to 0.1, 0.1 to 0.2, and 0.9 to 1. Finally, we get 10 buckets. Okay, then we measure how many buckets can be covered by these test cases. Okay, so the first coverage is structure-based neural coverage. So here we just consider the structure. We don't consider the value, the output of the neurons. And this activation-based, so we consider the output of the neurons. So these two things, so the ideas are very similar, so except for the distance calculation. For the structure-based, we use a G-cut calculation. For example, these are two paths. So then we measure, so this is the common neurons in these two paths, and this is the total neurons in these two paths. We just consider whether this neuron happen or exist in this path or not, just the structure. But for the activation base, so here the distance we use L2. Okay, so here the A is the activation value for the neurons in this path, and then we calculate the differences. So the difference can measure what is different decision logic triggered by this test case. So let me show some evaluation results. Okay, so here the first evaluation we want to demonstrate the accuracy and the effectiveness of the path abstraction. Because we do some abstraction, it may lose some precision. Okay, so here how to evaluate the path abstraction. So here we mask the critical path. Okay, we extract path, right? So for each image we mask this critical path and then to see the prediction change. Right? If the path is very important, after we mask it, okay, so the prediction will be different, so compared with the original prediction. So here the mask means we replace the output value with a 0. Okay, so making this path doesn't take effect. So here, so we show the 3 metrics. So first one is the width, right? So because with a different parameter, so the width of the path can be different. Okay, so we can ignore the first one. So the second part is the inconsistency after we mask the critical path. Okay, after we mask the critical path, we compare the prediction result with the original prediction. So we can see here, right? So the inconsistency is very, very high. So let's look at this large model. So the inconsistency is above 100%. It means this path is very important for the prediction. After we mask this one, okay, all prediction can be incorrect. So another one is inconsistency after we mask the other neurons, okay, except for the critical path, we mask the other neurons. So here you can see the inconsistency is very, very low. It means other neurons are not very important for the prediction. So the first evaluation is to understand the importance or the accuracy of the abstract path. So here are some examples. So we cluster the class 4 and class 5 into 4 clusters. And for each cluster, we can build we can create the abstract path. Okay, so you can see this is a path 1, path 2, path 3, and path 4. Okay, so for each cluster, you can see right, so they have a very similar style. So for example, this is a wide 4, right? So this is a rotated 4. Okay, so our path abstract path can represent the decision logic to recognize the different kind of images. Okay, so the second evaluation is we want to evaluate the correlation between the coverage and the bug or the defect detection. Right? So here the final goal is we want to apply the testing criteria to guide the test case generation. We want to find more bugs and more diverse bugs. So this is our objective. Okay? So here we generate a large number of the test suits. So each test suit we randomly insert some errors. So including the natural errors and the adversary examples. And then we evaluate the correlation between the coverage and the error rate. Okay, so here, so we can see when the coverage increases, so the error rate is also increasing. It shows compared with the existing structure-based coverage criteria, our criteria is more stable. Okay, so it can help us to generate the errors. So this table shows correlation between the coverage and the diversity of the errors. Right? For example, your testing tool can generate 10,000 errors, but all of these errors belong to one class. So then the diversity is a problem. Right? My testing tool only generated 100 errors, but they belong to the 10 classes. Okay, so then the diversity is good. Okay, so here, so you can see these are our testing criteria. So our result is much better than the existing one. So this is because we extract the path for different clusters. We want to maximize the behaviors we want to generate. So finally, yeah, it is more likely to find the errors belong to the different classes, belonging to the different clusters. Okay, so the second work is about the testing. So the model-based analysis and the testing for the stateful neural network. Right? So the first work is about the testing criteria. Second one, how can we apply the testing criteria to test? Okay. So the recurrent neural networks are proposed to handle the sequential data. So unlike the images, they have the fixed size. Okay. For the sequential data, the length is different. Right? For example, our text, audio, and the video. Right? So the length would be different. Okay. So here the recurrent neural network. So there's a loop in the So the network. It can handle the sequential data segment by segment. So for example, at each iteration, it reads one segment, like the segment 1. Okay, so then the recurrent network will output one hidden state, let's say H1. And then this H1 can be predicted as the output by the second segment, right? So segment, right? The recurrent network output H2. And then it can be translated to log. So finally, it can get the whole output. So the recurrent neural network is more complex than the feed-forward neural network, right? Because of the loop. Actually, this is consistent with the traditional program. So for traditional program, without loops, actually the program is very easy to be understood. The semantic is very, very simple. However, if you involve some loops, now the program semantics, right, become very, very complex. So the loops have been the very classical challenges for the traditional program analysis. So similarly, here due to the loops in the recurrent neural network, so it increases the complexity. So for example, for the feed-forward neural network, the number of the neurons are fixed, right? So but here, right, it depends on the number of the iteration. So for example, if your input, the length is 3, then this loop, right, so unroots 3 times. Okay, if the length is 5, this loop unroots 5 times. So finally, you can see the number of the neurons, right, is different. So depending on the length of the input, okay, it is more complex. So here our basic idea is we follow the idea from the traditional program analysis. We build the abstraction model. So this is the white box abstraction model, so which can be used to analyze the black box recurrent network. So the abstraction can largely reduce the complexity. So this is the basic idea. Okay, so here, similar with our testing criteria, so the training data is used to train the logic of the model. Right? So here we want to build the abstraction model based on the observation of the training data. So here, give a recurrent network, and we have the training data. So the first step is the profiling. So we predict each training data with the trained recurrent network. And for each training data, we can get output. Right? This is the sequence of the hidden states. Right? So this hidden state could be high dimension. Right? It is a high dimension vector. So we can use the PCA, so principal component analysis, to reduce the complexity of the vector. Okay, so finally, we can get a set of the simplified traces of the sequences. Okay, so each trace, right, is one observation for each training data. Okay, so based on these traces, we can apply the abstraction to build the abstract model. And this abstract model can be applied into the different applications. So for example, in this work, we use the abstract model to detect the adversarial examples. We use the abstract model to guide the test case generation. And in the ASE 20, we use the abstract model to analyze the robustness of the model. And in triple layer 21, we apply the model to explain the model behavior, to explain the model decision. And in the SML 21, we apply the model to guide the repair the errors we discover. And in the TIFS, so this is the security journal, so we use the abstract model to detect the backdoor in the model. So this abstract model is very powerful. It can be applied in different applications. Okay, so in this work, we apply the interval abstraction. Actually, you can apply the different kinds of the abstraction and build the different kind of abstract model. So here we use the interval abstraction to build a discrete time microchip. Okay, so here, this is a simplified traces, right? So then we use the interval abstraction, so which can split the space into some buckets. Oh, sorry. Into some buckets, right? So these 4 states are closed. So finally, right, these 4 states belong to this bucket. So the abstract state S0. So these 4 states are closed. They belong to the abstract S1. So finally, right, for this example, we extract 4 abstract states. And then we build an abstract transition. So for each pair of the abstract states, if there is one concrete transition, so for example, from S0 to S1, we have the concrete transition. Okay, so then there is an abstract transition between them. Except for the transition, we also calculate the probability. So for example, so the transition starting from S0, right? All transitions can transit to S1. So the probability is 1. So starting from S1, there are 4 transitions, but only one can transit to S0. So finally, right, so the probability is 0.25. Right? So finally, we can generate such an abstract model which can be applied to analyze the behavior of the black box recurrent network. Okay, so for example, here we have 2 inputs, 2 audios, which can be recognized by the to translate it to the text. Okay, so one is translated to this book is about science. Another one is this book about literature. So based on our abstract model, we can extract these 2 traces. Okay, you can see here, right? So the starting points are very similar, right? Because this book is about. So the last one is science and the literature. So you can see, right? So the last point, right? So they are different. Okay, so based on the abstract model, so now we can design some metrics. So these metrics can be used to analyze the recurrent network, the black box model. So for example, we design 2 kinds of the metrics. So one is a similarity matrix. So give any 2 inputs we want to analyze, so the differences, the decision difference, so for these 2 inputs. So for example, how many common states, how many common transitions can be covered by these 2 inputs. So give a set of the test cases, we want to measure the coverage. So for example, the basic state coverage, it means how many states can be covered, right? So in this abstract model can be covered by these test cases. So the basic transition coverage, so how many transitions can be covered, so by the test cases. So I will not introduce each one, so you can refer to our paper if you are interested in these metrics. So next I will introduce, right, so how to apply these metrics for the different applications. So the first one is to detect the adversarial example. So here I give 2 audios, so one is a benign and another one is a corresponding adversarial example. So let's see whether you can hear the volume.
Can I help you?
Yeah, so this one, can I help you, right, can be recognized by the recurrent network and translated to can I help you. And this one,
Can I help you?
okay, so from our human's perception, right, so we cannot distinguish the difference, but the model gives a very totally different text, right? Actually, this audio is generated by the state-of-the-art attacking tools, so the adversarial attack tool. Okay, so here the challenge is how can we detect if any input, this is an adversarial example or this is a benign example. Okay, so here our basic idea is we apply the text, use the text-to-speech engine to generate a reference sample. Okay, so using the text-to-speech engine, right? So this text we can generate a reference audio.
Can I help you?
Okay, then based on this text, we can generate another reference audio.
Ask Capital One to make a credit card payment.
Okay, so then we apply our similarity metric to analyze the similarity, right? So between this pair and between this pair. Okay, so here the basic assumption is the similarity for the benign pair, right? So it's very the similarity is very high, and the similarity for the adversarial example is very low. So this is because, right? So these 2 audios are benign audios, right? For the 2 benign audios, right? So their decision logic should be similar, but these 2. Right, this one actually is a benign because this is from text-to-speech engine. Right? This is a trustworthy engine. Then we assume this is a benign sample, but this one is an adversarial sample. So finally, their decision logic should be very different. So this is the assumption. Okay, so based on our observation, we find that it's true. So the similarity between the benign pairs is much higher than the adversarial pair. So finally, we can use this similarity to detect the adversarial example. So these 2 traces shows decision. So this is from our abstract model for the 2 audios. From our human perception, we cannot distinguish. Right? These 2 audios are very similar. But with our abstract model, we can clearly see the difference. Okay, so this is the first benign audio. This is the adversarial audio. So their behaviors in the recurrent network are totally different. Okay, so then we can detect, we can distinguish. We can also apply the coverage criteria to guide the test case generation. So this is a standard coverage guided workflow, actually very popular in the traditional software testing. So here we adapt this workflow to test the different networks. So here the basic idea is there's a set of initial states or the initial test cases. and then the mutation, at each iteration, it selects one state and use the mutation to generate the new test cases. Okay, so here we can apply the different transformations for the different domains like image, NLP, and audio. Okay, so these new test cases, we want to maximize the coverage because we want to maximize the diversity of to test the different behaviors of the model. Okay, so here we will, for the feed-forward network in Deep Hunter, we use the neural-based coverage. For the Deep Stella recurrent neural network, we apply the abstract model, right, like the basic state coverage, to calculate the coverage and to check whether some new behaviors have been discovered. If yes, so the inputs will be added into the seed pool. Otherwise, so the test cases will be removed, will be discarded because they cannot trigger any new behaviors. So finally, with this loop, we can explore the behaviors, the different decision behaviors for the deep network, and finally, we can find more bugs. So the last work, right? So in the second one, we have discovered some bugs, right, based on the testing tool. So the last one, how can we automatically repair this problem? Okay, so this is still the model-based analysis for the recurrent network. So in the last work, we still have two issues which are not addressed very well. So the first one is, right, so we use the interval abstraction, but it may not be precise. So for example, so these states, right, so are very close, but with the interval abstraction, they will belong to the different abstract state. Okay, another one is we still, right, cannot easily understand the semantic of the model. So for example, what is the semantic of each state? Okay, so these are still remaining issues in the previous work. So in this work, we addressed these two problems and we apply this abstract model for the automatic repair. So the basic idea, right, so in the previous part is similar. Okay, so we just get the traces, and here we use a clustering-based abstraction, which can group the similar states into one abstract state. Okay, and based on this, right, so here are some errors we discovered from the testing tool. We want to fix to repair these errors automatically. Okay, so then we apply the abstract model, right, do the influence analysis. We want to identify the responsible training data. It means the training data should be responsible for these errors. Okay, then based on this responsible training data, we can generate the new data. So finally, the new data can be applied to repair this model. So this is the basic idea. So let's say the semantics of the abstract state. So here we mainly focus on the classification task, right? So here the H is the hidden state. So then the function F, which can map the hidden state to the final output. For example, for the classification, so here the output is a class. Okay, so for the generation, right, so the output is another different output. So let's say this is an abstract state, right? So there are 10,000 concrete states inside this abstract state. So we apply this function F to predict each concrete abstract, each concrete state. Okay, so finally we know how many states can be classified as 0, how many states can be classified as 1, different classes. Okay, so then we can calculate a confidence score for each class. So for example, there are 100 states, right, predicted as 0. So then the confidence is 0.01. So most of the states, so 9,500 states are predicted as 1, so the confidence is 0.95. Okay, so finally we can build a stronger relation between the abstract state and the classes. So for example, right, so when one concrete state falls into this abstract state, so then we know it is very confident, right, so 0.95, right, so this state can be predicted as 1. So we built the relation between the abstract state and the predicted class. So let me give you one example to understand the semantics of the abstract states. So here we train a recurrent network to recognize the image, the images. Okay. So at each iteration of the recurrent network, it reads only one rule in the image. So for example, so in the time 9, so the recurrent network reads the first 9 rules of the image, right? So the 1 rule, 2, 3, 5, right? It only recognizes the 9. And then in the 28, it can read the whole image. Okay, so let's see the abstract state and the confidence score. So at the time 9, the RN can only read the first 9 rules, right? It is not allowed, so we cannot easily recognize, right? So you can see here, so the 7, right? So this is the level 7. So it has the highest confidence, so 0.35, but it's still not allowed, right? Because the model can only see a small part of the image. Okay, so this is the prediction, the recurrent network. It is predicted as 7, and the probability is 0.21. Yeah, not very high. So let's say the 13. So now we can see more about this image, right? So now it seems like 3 or 2, right, or 8, right? So here you can see the confidence score. So 2 is a 0.378, right? So 3 is 0.176. Okay, so let's say the prediction of the recurrent network is 2, but the probability is very high, 0.89. Okay, so here actually, so the probability is not a good indicator for the confidence. So the softmax actually is not trustworthy. But our confidence with the abstract model is more stable because it is based on statistical information from the training data. Okay, so after the, let's say the last one, so 28, right? So the model has read the whole image. So now we can see the 8, the confidence is very, very high, so 0.977. Okay, so we can see during the whole process of the prediction. Okay, so with abstract state, right? So the prediction is similar, is consistent with our human's perception. Okay, so this is the semantics of the abstract state. Okay, so based on the state abstraction and the semantic of the abstract model, so next we develop the lightweight influence analysis. Give any so test data, we want to identify the training data, so which are most influential or more important for the prediction of this test data. Okay, so here we developed two. One is a sample level influence analysis. We want to identify the training data which should be responsible for the prediction of the whole sample. Right? So this is the sequential data X, including some segment X1, X2, Xn. Okay, another one is a segment level influence analysis. Right? Sometimes we don't want to see the influence for the whole prediction. We just want to see the influence for only one of the segment. Because maybe this segment is not so well predicted. We just want to see which training data should be responsible for the prediction of this segment. So these are difference. So let's first look at how to calculate the segment level influence analysis. So give any training data, So this is the one training data X, including some segments. So after the recurrent network, we can get some hidden states. Okay, so each hidden state we can map to each abstract state. So finally, we can get a trace. This is a state transition. So for example, from the state Q0 to Q1. So after we get the segment X1, it can transit to Q1. Okay, and then to Q2, and finally to Qn. All right, so here intuitively, so this training data should be responsible for the prediction of each segment here, X1, X2, Xn. So based on this one, we can update the influence function. Okay, so for each segment Xi, so it is under the abstract state Q-1. So finally, so we know this X should be responsible for this prediction. So next time if you want to identify which training data should be responsible for the prediction of the Xi under Q-1, then X will be one of such responsible training data. Okay, so here the abstract state is very important. It represents the different context information. So let me give you one example. So here, so we have two sentences. So here the point, so they are the same segment, but they have different semantics because they belong to the different contexts. Okay, so here our abstract state can represent the context for the different segments. So for example, X is responsible for the prediction Xi under the Q-1, but it is not responsible for the prediction of Xi under another abstract state. Okay, so this is the context represented by our abstract state. So sample level influence analysis, we want to identify the training data which is influential or responsible for the prediction of the whole test data, so like the image. Okay, so the basic idea is very similar. We just to extract the temporal features from our abstract states, and then we compare the similarity of each training data with test data. Okay, so the highest, so training data will be the most influential, or will be the most responsible one for the prediction of the test data. Okay, so here for the temporal feature, so we extract the trace first. And for each abstract state, we extract the three typo. This is the three typo feature, So including first the unique identifier, the abstract states. And the second one is the confidence scores, So these are the confidence scores. It represents the decision behaviors, so in this abstract state. And the third one is the prediction results, so for example 7. Okay, so finally we can extract the temporal feature. This is the whole temporal feature. And we use this feature to measure the similarity for this decision. Okay, so based on the inference analysis, now let's see how to repair these errors. So first, this is the sample level repair based on the sample level inference analysis. So here, this red circle is misclassified as triangle. So with our inference analysis, we can identify, so this triangle, right, is more close, right, so to this, so this red circle, right, this is Y, so this red circle can be misclassified as a triangle. Okay, so then how to mitigate this problem? We just need to generate, right, so these yellow circles, which are more close, right, so to the red circle than this green triangle. So finally, so these yellow circles can have to, right, so fine-tune this decision boundary and to fix so this error. Okay, this is the segment level repair, right? Sometimes, especially for the sentiment analysis, like the natural language, right? So one segment can make the prediction incorrect. Okay, so here we use a segment level inference analysis to localize the segment, which could be the root cause for this invalid prediction. Okay, so here the basic idea is for each segment, if the number of the responsible training data is very, very low, it means, right, so the training data is not enough for the prediction of this segment, then it is more likely to be predicted incorrectly. All right, so here let's see this example. So this is the sentence. This sentence is actually positive, but misclassified as negative. Okay, so here we show the state transition. So from state 1 and reading the segment just to state 2, and to state 3 and to state 9. So for each segment, I show two numbers. Okay, so the first number is the prediction result. So 1 indicates this is a positive, and 0 indicates this is a negative. And another number is how many responsible training data we can identify for this prediction. So you can see here, this is 43. It means for the prediction of the just on the abstract state 1, we have found 43 training data. Okay, so let's say for this segment, loose, now you can see this number is 0. It means, right, in the training data, this model never see the prediction for this segment, so under the abstract state 7. Okay, so finally the prediction result, right, becomes from 1 to 0. So this is the root cause why this sentence cannot be predicted well. Okay, so how to mitigate this problem, how to repair this problem? We just to identify the responsible training samples, and then we find the position. Okay, so this responsible training data can reach 7. Okay, after the 7, we can insert the loose. Right, it's very simple. We just let the model can see the unseen segments. So finally, it can mitigate this problem. So here are some evaluation results. So first one is the sample level repair. So we just use the repair on the MNIST classification. So here we identify 23 field inputs. So these inputs are very difficult to be to recognize by the model. Even for our human, it's not easy. Okay, so based on our influence analysis, we generate 161 new inputs. These are like the yellow circles, which can be applied to fix these errors. Okay, so here we use the inference analysis first to extract 23 training data, and based on this 23 training data, we randomly generate a large number of the inputs, and then we select only the top 161 inputs which are more close to our field inputs. So let's see the comparison. So we compare our method with a random repair. So for the random, it randomly selects 161 inputs. But for our method, we select based on the guidance of the influence function, the influence analysis. So finally, we can repair about half of these errors. The random only repairs 18.7 of the errors. So this is the result about the segment level to repair. We apply it into the segment analysis. This is because the error is caused by the prediction of some segments. Okay, so again, we compare our method with a random. So we select some influential training sample. And for our method, we localize the abstract state. And after this abstract state, we insert the different segments. But for the random, in the same training data, it randomly selects one position and insert the training data. Insert the segments. So these are the difference between the random strategy and our method. So you can see our method can achieve the much better result in terms of repair. So each column we also show how many influential training samples we collect for the repair. So you can see when we augment more training data, of course the repair rate is better. Okay, so this is today's my talk. So I mainly introduce 3 words. So one is about the testing criteria. So how to measure the diversity, right? So triggered by the test cases and apply the testing criteria so we can test the different kinds of neural networks and the kind of neural network. And then after the testing, how to repair the testing results. Okay, so this is a big picture, right? So actually, right, to build the trustworthy AI system, deep learning system, right, we still need a lot of effort. So this is a secure deep learning engineering life cycle. So we can see the requirement analysis, data, right, so label, so in design, training, testing, deployment, and the evaluation. So today I merely introduce these 2 parts, right, software development and deployment. Actually, right, so they are still, right, so in each step we can provide so the techniques, the tool chains to guarantee the quality, right? So it is still bit if we only analyze the quality and the security on the model level. So for the developers, we need to provide the guarantee, right, so in each step. For example, in the requirement analysis, we can give some suggestion. So for the data collection, right, so we can monitor to the data quality. So in each step, we should give the intern so feedback so for the development. So this is from the life cycle. So from the system level, right, so the model is just one component of the system. So your system can have multiple models. Sometimes you can have the traditional software component. So they work together to build this system. Okay, so we need to guarantee the quality of the whole system to consider the interaction between the different components, different models. Okay, the third one is about the framework level. We need to consider the underlying, the fundamental framework, so like the TensorFlow, like the PyTorch. And also the model is trained with the limited training data. Okay, so we need to provide some runtime monitoring. Okay, if some inputs cannot be handled or is handled uncertainly, right, so by the model, so then we need to give the alert to make sure the model only handles, right, so some inputs which are certain, are confident. So it is not easy. It requires the knowledge from the different domains, right, so like the AI, hardware, software engineering, and the security. Okay, so I think that's all. So any questions?
Any question?
Yeah, thank you for this impressive talk, actually. I have one question regarding the recurrent neural network part. So, you mentioned that you parse the data, then you extract the hidden state, then you apply principal component analysis. First, actually regarding the recurrent neural network, as far as I know, although you mentioned that it keeps collapsing, according to with the time, so the more data it unroll.
Okay.
But the parameters are shared, so they are the same parameters.
Sure. Yeah, you are true.
So they are not new parameters.
Yeah, actually it is not a new neural.
Yes.
The neural is the back, but the neural output can be different.
Yes.
Yeah, so
according to the because the input is different, right?
Yeah, this is the point. So in the existing testing criteria, the neural-based coverage, right? They only consider once for the neural output. But for the recurrent network, right? So in different iterations, it can have the different output.
Exactly.
Then it can have the different activation. So even for the same neural, it can have different numbers of the output. Then it is not easy to analyze by the existing. Yeah. So
Okay.
This is why we want to do the abstract model.
I see.
Yeah.
I see.
So you don't know, right? How many outputs, right? Can be.
Exactly. Yeah.
Yeah, that's true. Actually, it's not the real neural. It's just a different output.
Okay. Yeah, the output is different.
Yeah.
Yeah, this is one thing. So regarding, so you mentioned you extract the hidden states. So these hidden states actually how because to extract the hidden state you need to train the recurrent neural network.
Yeah.
But I think the PCA and the state are usually calculated separately. It's not end to end, right?
Yeah,
so
but actually, yes.
you
For the testing, this is offline. So your model has been trained, and then we just collect the output. So for example, if the hidden state the size can be 2048, right?
okay.
So then we apply the PCA to reduce it to the 3 or 4. This is the offline thing. Yeah.
Okay, so this
Not
is
in
not
the
in
training,
the,
not in the
okay, in the
training.
evaluation step. Yeah, but in the training step, you trained it normally with the normal like if it's a
Yes, for the
classification?
training we don't, so as our technique only to analyze the existing model.
Okay,
We don't know
okay.
how it is changed.
I see,
we
I
just
see, I
select
see.
the model to analyze.
Okay, so it's after training you just analyze what's happening with a new testing
right,
data.
that's true.
Okay. Yeah. My second question regarding PCA and using like discrete mark chain.
Yeah.
You know, RNN itself can be considered as an advanced version of, although it's a black box.
Yeah.
So my thinking. So because you do the analysis, you get some results. Can you include some of these like findings or objectives during the training to make the model less black box?
Yeah, this is good. This is good question. Very good question. So actually, recently we have a paper about the guiding of the reinforcement learning model. Yeah, I think this is similar for the recurrent network. Okay, so here we can use abstract model, right? So abstract state to give some guidance for the training. So for example, for the recurrent network, so the reward is a problem, right? So the reward is very sparse. But based on our abstraction, we can monitor this is a good abstract state, or this is a bad abstract state. You can quantify to give some score, like this is a 0. Okay, so for when your these traits can reach this abstract state, then you can give more reward. So it is reinforcement learning. But for the recurrent network, I think so we can borrow this idea. So for example, if you can monitor, right, so the training process, if this batch or can reach some good abstract state, okay, so then you can give more. So the loss can, right, you can design some loss based on the abstract state. But it is very expensive. Actually, we consider this idea, but for the training, if you update the abstract state in the training process, it is expensive. So how to balance the, but this is, of course, is a very good question.
Yes, that's quite interesting actually.
This is the semantics of the abstract state, right? So we want to make sure, right? So each abstract state should be related to one class. You should be very, very certain, right? So this abstract now is about, for example, class 1, class 2, class 3. If the abstract state is uncertain, then during the training process, you should, right? So try to avoid such abstract state.
Okay.
But
okay.
yeah, of course, it still needs some observation and needs some.
Yes. Because you mentioned also one issue regarding the confidence level. Softmax usually overconfident, and we cannot rely on this to provide some uncertainty quantification.
So I think here we have, I missed some details. Actually, we have a refinement for the abstract model. So for example, so here, of course, you can cluster abstract states to 5 abstract states or 10 or 12. Okay, so here we want to maximize the whole confidence. So for each abstract state, right, so you can calculate the average score. Okay, so finally we want to find a number for the abstract state such that the total, the sum of the average scores are very, very high.
Okay.
Make sure your abstraction is precise.
Okay, yes, I see.
We also have some experiments show that this is a good indicator.
Okay,
It means in the training process you can also try to increase the average confidence for each abstract state.
Yeah, exactly. Because this is an issue recently, you know, like especially with these softmax or deep neural networks that are trained based on softmax, and some people rely on the predicted probability for a confidence.
Yeah, but it is not.
Yes, so I see this like, you mentioned even here that abstract states can have some more accurate confidence compared to the softmax.
Sometimes, it is over, so for the probability, it is overconfident.
I see, okay. But I see also this is an interesting direction regarding the providing robust uncertainty quantification, which is one of the trustworthy. Yes, okay, thank you. Thank you.
Thank you for sharing your interesting work. I have a couple of questions for the first part of the talk.
Testing criteria, the
yes.
pass rate.
Right. So I don't know whether my understanding is correct. So the total number of paths, once you have a fixed number of neurons. And I suppose the total number of paths are fixed. Let's say, for example, if you have a tree.
Yeah, actually I have backups, right? Okay, so this is the so how to extract the path for each image.
Right.
So
my,
here,
my understanding is that the total number of possible paths
yeah,
are fixed. It's just a
this is just a combination of different neurons.
yes.
Yeah, you are true. Yeah.
Then,
But it is the space is very
very large.
Yeah,
Yes.
very large. Yeah.
Then I don't know why training data is used to calculate the number of paths. Let's say I have another method. I just count how many number of paths covered by a particular test.
Yeah, this is a good question. So your question is why we need to use the training data to provide.
Yeah.
Okay, so here the basic assumption is your model is trained from the training data.
Right.
Okay, so here, so the logic is learned from this training data. So we use this training data to provide to build the basic. Yeah, of course, this training data may not be enough, right? Sometimes your model can generalize to other data that right? So it's different with the training data.
Right.
Okay, so then you may need to, for example, we can generate some testing data which have a totally different path.
Right.
Then you may update so this abstract path. Yeah, this is the new behaviors training data cannot represent. Then we need some other data to reflect.
Yeah. Okay.
Yeah.
So it's also possible that I just blindly I don't use any training data. I just let's see.
Enumerate, maybe.
I just count for each test. I count the number for which part is covered.
Okay.
For, let's say many tests.
Okay.
And I just count how many distinct parts.
Yeah.
Then I
Okay,
claim that.
this is a good awesome. Yeah, so then you will maintain your existing test set, right? Compare with the existing test set to make sure, right? So it can grow larger and larger.
Yeah.
So finally, this is also true. Yeah.
Oh.
So here, I think the idea in general is similar, but we just avoid to cover the paths that have been triggered by the training data.
Yeah. Okay.
But your point is you start from the zero, right? So empty
Right.
set. There we just give the training data as the starting point.
Okay.
Yeah.
Yeah. Thank you. Another question is how the bug is identified.
Yeah, this is another very good question. Yeah. So here, actually, for the deep network, we can easily identify many adversary examples. Yeah, even you use a random, you don't use the guidance of the testing criteria, right? So you can easily generate a lot of number. So here, so ongoing research is we want to classify to category to look at error category. For example, you generate 1,000 errors. Okay, maybe this 100 errors, right? They have the similar root causes. This 100 they have the similar cause. So finally, we don't want to report the number of the errors. We want to report to the categories, how many classes of the errors. Then for each class, then we want to say, okay, how to fix this one. Is it possible, right, to use different techniques to fix?
Okay.
Yeah, and for the total number, it is a lot, really a lot. Yeah.
Yeah. Thank you.
Yes, thank you for the question.